You know what it means to take the mean of something, right? Yeah. You add up the numbers and divide them by how many there were. So let's say we had 4, 5, 8, 3, 2, and 2. What does that average out to? What's the arithmetic mean of that? What'd you get? 4. Okay. I don't know if you've ever thought about this physically or not, but 4 is what you would get if you squished them all down, right? If I took this here and put it over here, here, and then I took this one and put it here, and then I took these 3 right here and put it here, it comes out to 4. That's what arithmetic mean is. Another way to look at it is, let's say that you have a fulcrum here and a board here. Okay, and it's perfectly balanced now. But if I put something here, now it's going to go down on this side, right? And if I put 2 of them here, what would I have to do to balance it out over here? I would have to put 2 of them here. What else could I do? Yeah. Specifically, here. Because this is 2 plus 2, and this is 1, 2, 3, 4, and now it's balanced. If you use these as negative numbers and these as positive numbers, the average would be, or the mean would be 0, and that would balance it out perfectly. So there are physical ways and visual ways that you can represent this. Now, what we did the other day, you had a right triangle that was created from a full piece of paper. Draw the altitude, the height of the triangle, and the diagonal that you cut as the base. We actually see 3 different triangles. Okay? And in fact, what I'm going to do is I'm going to say we have this triangle here, we have this triangle here, and together we have this triangle over here, because these 2 are identical. All 3 of these triangles are similar. Here's an angle. That's matching up perfectly. Here's another angle that matches up perfectly. So I have a right angle here, and I have this angle. I have angle-angle similarity. So that proves these 2 triangles are similar. And same thing happens over here. I got 90 degrees here. This is going to match perfectly, right? I have this triangle here is also similar to this triangle. And then we started talking about the ratios that went together. If we call this A, and we call this B, and we call this C, and we call this D, and we call this E, the ratios that have to work together, obviously D and E have to work together because they are both the longest, they're the hypotenuses. And A is the shorter one on this triangle, and C is the shorter one on this triangle, so they have to go together as well. And then B is the middle, and C is the middle on this one. So depending on which triangle you're looking at, C might be the smallest side or the medium side. It means that if I compare C to B, I'd have to compare A to C over here. The rules of proportion say that this proportion would also be true. And we can come up with numbers that will work here. The book defines geometric mean as the number that would go here in order to make this true. But what I showed you on here was that if we cut this and match them up like this, what we said was this was C right here, and so is this. So this piece is a square. And this over here is a rectangle with B and D as its pieces. And we said that because of this, if I multiply these two together, AB is equal to C squared. So that meant the rectangle that got formed with these two was equal to the square that got formed here. The area of this rectangle, if you wanted to squish it out and make a square out of it, would fit exactly in here. So just like when we did numerical or arithmetic mean, we were dealing just with height, right? Just the one dimension here, and everything got squished. That would be the height. Here, it might not squish perfectly. C might not be a rational number, but C squared is going to equal B times A. Okay. So if you want, you can think of geometric mean as the size of the square that you would have to make if you were evening out two other numbers. So, for example, if this is 12 and this is 3, how long does this have to be?
6.
Right. 12 times 3 would be 36. This would be the square root of that. Now, I've said that, but let's see if that even works. Because it's one thing for me to say it, but it's an entirely different thing for it to pan out when you do some of the other stuff that we know we have to be able to do. These are right triangles. You guys remember the Pythagorean theorem? Right? It says that this squared plus this squared has to equal this squared. Okay. So this is 6 squared, 36. This is 3 squared, right? 9. Square root of that would be the square root of 45. Do you know how to simplify that? Yeah.
3 and square root 5.
Yeah. Okay. This is now, for this triangle, if this is 3 and this is 6, this is 3 times the square root of 5. Yeah.
Wait, why is it 3 and the square root of 5?
Okay. So 45 is equal to, if I took all of the prime factors, it would be 3 times 3 times 5. We okay with that? And that means I can break this up. This is 3 squared, and this is 5, and you multiply them together. That's one of the rules of radicals, right? And 3 squared, if you take the square root of 3 squared, that's 3. Remember, this is a squared plus b squared equals c squared. That means we have to square this number and square this number and add them together, and it will be equal to the square of this number here. What's 6 squared?
36.
Okay, and what's 12 squared? 144. And if you add them together, what do you get? 180. So we're talking about taking the square root of 180. Let me just go through this with you and talk about a really, really simple and easy way to do this. Do you guys know what the prime numbers are? What's the smallest prime number? 2. And then? No. 3. And then? And then? Okay. And then 11. Okay? It's more than we're going to need. Do you know how to tell if a number is divisible by 2? Even number. And how can you tell really quickly? 7, 4, 3, 5, 6, 8. Is that an even number? Yes. How do you know? Right. You look at the last number, and if it's divisible by 2, then the whole number is divisible by 2, right? Okay, great. Do you know how to tell if a number is divisible by 3?
If you add everything together and if that's like divisible by 3.
Right. So 3,654? What does that add up to? 3 plus 6 plus 5 plus 4. 18. Is that divisible by 3? Yeah. Then so is this. Okay? Do you know how to tell if a number is divisible by 5? It ends in 0 or 5. Okay, now, let's go back. We want to take 180, and we want to get the prime factors. Will 2 go into this?
Yeah.
Okay, and what do I get? 90. Will 2 go into this? What do I get? 45. So in other words, I'm going to keep going with 2's until I can't anymore. And then I'm going to go to the next prime number, which is 3. Will 3 go into this?
Yes.
Okay. What do I get?
15.
Will 3 go into that?
Yes.
What do I get?
5.
Okay. Now, if I took 2 times 2 times 3 times 3 times 5, and I stopped at 5 because it's a prime number, that would give me 180. Right? Because I divided, so if I multiplied them back together, 5 times 3 is 15, 15 times 3 is 45, 45 times 2 is 90, 90 times 2 is 180. I now have the prime factors of 180. 2 squared times 3 squared times 5. Those are the prime factors. Okay? Now, if I want the square root of 180, well, we just said 180 is equal to 2 squared times 3 squared times 5. And we know from the rules of this thing, right, the rules of radicals, that this is square root of 2 squared times square root of 3 squared times square root of 5. And we know that if you're taking the square root of a square, you get a 2. Here you get a 3, and here you get the square root of 5. So the answer to this is 6 times the square root of 5. But here's what we figured out. What we figured out was that this was 12, this was 3. We made an educated guess because of what we'd done before that if we multiplied these two together and took the square root, we would get 6. So then we said this has to be 12, this has to be 6, this has to be 3, that has to be 6. Then we did the Pythagorean theorem to find out that this was 3 square root of 5, and this one over here was 6 square root of 5. Is that right? Okay. Well, now, that means we have this triangle right here, the big one, where this is 3 times the square root of 5. This is 6 times the square root of 5. And what's the bottom from side to side? 15, right? Because it was 12 and 3. Is that right?
Yeah.
Okay. So what I would like you to do now, if this is going to work, since this is also a right triangle, this squared plus this squared has to equal that squared. Check it out. Okay. 6 times the square root of 5. What did that turn out to when you squared it?
I got 36 times 5.
Which is what?
180.
Okay.
And then the other one, I got 9 times 5.
Which is?
45.
Okay, and when you added them together, what did you get?
225.
225. And when you squared 15, what did you get?
It works.
It works. Right? If I square this, it equals 225. Your textbook simply defines all of this in terms of the simple ratio, right? A over x is equal to x over b, and the geometric mean of a and b is whatever x makes this true. But if you actually think about a times b is equal to x squared, and x is equal to the square root of a times b, what that really says is, if I take a times b and get the area of that rectangle, and then I try to make it into a square, the length of that square will be x. And it works out physically here when you do this, and it works out numerically, and we could start cutting out rectangles and then trying to figure out how to take those rectangles and turn them into squares.